From Earth, the night sky appears ethereal, peaceful. It's so far removed from human civilization, you'd be forgiven for thinking we're immune to anything going on up there. But that couldn't be further from the truth. We are under attack. Cosmic rays are bombarding us from every direction. Tiny particles that collide with our planet's atmosphere, setting off a chain reaction of ionization that can render our satellites and other electronic machinery useless. But where do they come from? For hundreds of years, astrophysicists have searched in vain to find the origin of these elusive attackers with little success. Even the type of source has evaded their searches. But now, thanks to a whole new field of research, we're starting to find answers. Not only do we now know what to look for, but they are proving more powerful than we ever imagined. What in the cosmos is possibly capable of producing a quadrillion electron volts of energy? I'm Alex McColgan, and you're watching Astrum. Join me as we follow the trail of cosmic rays, leading us right to the limits of physics as we know it. We'll see how scientists detect the highest energy particles in the universe and meet a new class of astronomical objects whose extreme behavior, until recently, seemed like the stuff of science fiction. The Milky Way is full of energy, but our eyes can only detect a tiny fraction of it. Beyond the spectrum of visible light, charged particles can give off higher energy radiation in the form of X-rays and gamma rays, creating a mess of energetic fingerprints throughout space. Astronomers can forensically decode these cosmic clues to understand the flow of energy through our galaxy. But among these charged particles, there is one group in particular that remains clouded in mystery. Back in 1912, the Austrian physicist Victor Hess made a historic air balloon ascent up to 5,300 meters, where he could measure the rate of ionization in the upper atmosphere, or how quickly atoms and molecules are becoming charged. He expected to find that it decreased at higher altitudes, confirming the prevailing theories at the time. However, this was not to be. Unexpectedly, Hess recorded a rate of ionization that reached 3 times higher than at sea level. This led to the realization that the ionizing radiation he had dedicated his career to studying came not from Earth, but from space. He had discovered cosmic rays, and they did not come in peace. Earth is under constant barrage from them. These high-energy particles, mostly protons, travel at nearly the speed of light and collide with our planet's atmosphere, sending a shower of secondary particles down onto its surface. These attacks can do some serious damage. The secondary particles produced in cosmic ray showers, the likes of muons, neutrons, electrons, positrons, and gamma rays, can interact with living organisms, contributing to genetic mutations and radiation damage. And when cosmic rays interact with satellites or other orbiting electronics, they can trigger a bout of ionization that can cause the circuits to degrade or even fail catastrophically. And they are not only a nuisance to our best space equipment. Cosmic rays have meddled with our best scientists too. For more than 100 years, the question of where cosmic rays come from has been one of the major unsolved mysteries in high-energy astrophysics. Their physical properties make them almost impossible to track. Magnetic fields bend their path before we can locate their origin, and they break down into a shower of particles before we can learn their identity. These challenges are laid bare when scientists try to measure the cosmic ray spectrum. If you plot the number of incoming high-energy particles as a function of their energy, you notice a distinct steepening point known as the knee, beyond which the really high-energy cosmic rays above 4 peta-electron volts are much less common. At first, some scientists assumed that this knee must mark the boundary between cosmic rays coming from inside our Milky Way and those coming from beyond. Others simply didn't know. But just as scientists were about to accept defeat, one observatory stepped in to revolutionize the search for these sneaky interlopers. Before I start revealing the mystery, want to have a crack at it yourself? Of course you'll need the right equipment, but even if you don't have a full observatory in your backyard, you can still see the wonders of the universe, galaxies, or the remnants of dead stars like the Crab Nebula in incredible detail using the Dwarf Mini Telescope, who've kindly sponsored this video. Check out this image of the Crab Nebula taken by one user, Julia Resch, using this book-sized ultra-portable telescope. Julia only had a small window to take this image, as it had been the first clear night in 4 weeks, and there was work in the morning, but just look at the results she achieved. This was thanks to the Dwarf Mini's ability to auto-track stars, letting it quickly orient itself towards your preferred target and its live stacking function. By overlapping multiple photos, it produces these really clear images of beautiful deep space objects in our cosmos. I'm a big fan of this telescope and can't recommend this enough for someone who's looking to get into astronomy. So scan our QR code or follow the link in the description below to see for yourself. Astronomy enthusiasts who use the code Astrum5 at checkout get 5% off their purchase. Now, enough waiting. It's time to take a look at the observatory that's helping solve the mysteries of these incredibly high-energy cosmic rays. The Large High Altitude Air Shower Observatory is a ground-based observatory located nearly 4,500 meters above sea level in the mountains of Sichuan Province, China. It has one main objective: to find the highest energy particles in the universe. The chief scientist on this mission is Professor Zhen Cao, who gave Astrum an exclusive interview about LASSO's work. He said, "To make good measurements for the knee of the cosmic ray spectrum, you need two things. The detector must be big enough, and it must be able to identify the original particle from the air shower it creates. Cosmic rays become more rare the higher the energy. For the highest energy particles, less than 1 per square kilometer per century is expected to hit Earth. To combat this issue, you need detectors spanning a whole lot more than a square kilometer, which is why LASSO covers an area the size of 190 football fields. As for identifying the particles, I mentioned that the cosmic rays produce a shower of secondary particles when they collide with the atmosphere, and this is what scientists use. They must essentially piece the debris together to work out whether the original particle was a proton, a helium nucleus, or something heavier. This is a tricky process, as you need to make sure you catch all the fallout. But LASSO is one of the most well-equipped observatories to tackle the challenge. It has at least 3 types of interconnected detectors in an array to capture the shower and then identify the original cosmic ray particle. This unparalleled ability pretty quickly led to the team's first big discovery. Professor Cao said, "At the time, we only had around half of LASSO built. We put it into operation for around half a year and suddenly found that there were so many gamma rays. By 2021, LASSO had detected gamma ray photons with energies exceeding 1 peta-electron volt, or 1 quadrillion electron volts, and one at 1.4 quadrillion electron volts, making it the highest energy photon ever observed. For context, that's nearly 150 times more energy than the fastest protons accelerated by the Large Hadron Collider." Now, the laws of energy conservation tell us that peta-electron volt particles don't just appear out of nowhere. That colossal amount of energy has to be transferred to the particles from a source. Scientists have been theorizing about such a source for decades, but LASSO's finding proved its existence once and for all: the Pevatron. Pevatrons are any source capable of accelerating particles to a peta-electron volt of energy, and their existence promised to revolutionize the hunt for cosmic rays. But how do we find them? Luckily, LASSO wasn't finished. Gamma rays are useful because they are neutral in terms of their charge, so they can travel in straight lines throughout the universe without being bent by magnetic fields. This added a new dimension to LASSO's work. it could trace back to where the gamma rays had come from. Mapping these traces across the sky, scientists identified 12 distinct sources capable of producing ultra-high energy gamma rays, several of which showed signs of accelerating particles to a quadrillion electron volts. There was a catch though. Lasso may have identified the general direction of these gamma ray sources, but scientists had no idea how far away they were. 12 lines of sight stretching out endlessly into space isn't exactly a narrow search field. Except, scientists knew something else about these gamma rays that would tighten the net. The universe has been full of photons since the Big Bang, and these photons are very cold with low energies. Gamma rays at ultra high energies are very likely to collide with these background photons, and when they do, they vanish. This means that gamma rays simply can't travel vast distances through space. So, if Lasso was detecting them here on Earth, then they couldn't have traveled very far. In fact, there is no way that these 12 high energy sources could be extragalactic. They must be inside our Milky Way. Not only did this tell scientists that the knee, the bend in the graph we saw earlier, had nothing to do with cosmic rays coming from outside the Milky Way, but it brought the search for them much closer to home. The race was on. Now, before Lasso's work, astrophysicists had developed theories about the production of cosmic rays and which type of source could be responsible. After all, space is a weird and wonderful place, home to several unusual objects displaying extreme behavior. But which of these oddities were capable of producing the highest energy particles, and how? For the past 70 years, a popular idea was that supernova remnants played a key role in producing cosmic rays. They certainly have enough energy for it. In fact, calculations show that if they converted just 10 to 20% of their kinetic energy into accelerated particles, supernova remnants could supply most of the cosmic rays we see in our galaxy. See, when a star goes supernova, it drives material out into interstellar space, forming a collisionless shockwave just ahead of it, where there is a sharp change in density, magnetic fields, and pressure. When a particle hits this shockwave, it gets bounced back and forth across the shock front, gaining energy each time. Particles can propagate here for some time, up to thousands of years, and the longer they spend there, the higher their energy can become. This process is known as diffusive shock acceleration, or the Fermi mechanism. But although supernova remnants can accelerate particles in this way, reaching peta-electron volt energies may still be tricky. Theoretical models suggest that supernova remnants are only capable of accelerating particles to these extremes during the first 100 years of their life, and all the supernova remnants we know of are much older. However, there might be one scenario where supernova remnants can act as a source for ultra-high energy gamma rays. If they gain enough energy to overpower the magnetic forces that confine them, some accelerated particles may escape the supernova remnant and get trapped in nearby giant molecular clouds. Here, they can interact with the dense gas and produce gamma rays with energies up to 1 quadrillion electron volts, even if the supernova remnant itself is no longer capable of peta-electron volt acceleration. So, supernova remnants show some potential as cosmic ray producers. Up to 6 of the 12 Lasso candidates could be associated with them, but they're not the main type of source we should be looking at. There's another source capable of creating even higher energies: pulsars. We've covered pulsars on the channel before, so feel free to check out some of the previous videos for more information. But as a quick recap, pulsars are highly magnetized, rotating neutron stars created in supernova explosions. We have now detected over 1,500 pulsars. But how could they create such high power gamma rays? Well, they're already proven to be capable of accelerating electrons and positrons, since the dense and highly magnetized structure rotates to produce powerful electric fields. These electric fields can strip electrons from the star's surface, forming a wind of particles that expands outwards at rapid speeds. And once this wind reaches the surrounding material, like the gas or dust from a nebula, it suddenly slows down, forming a termination shock. At this shock point, the particles are accelerated to extremely high energies. You can think of it like water flowing in a stream. Normally, the flow is smooth, but if you place an obstacle in the way, some water will spill out, and this water will be flowing much faster. The LASSO team believe that more than 30% of the candidate Pevatrons they detected could be associated with pulsars, making them a key player in the search for cosmic rays. The final type of cosmic ray source came as a bit of a surprise to scientists. If we take another look at the spectrum and zoom into the knee shape, you see not a smooth line, but a hump. In other words, an anomaly. The properties of these cosmic rays didn't fit with them coming from a known source like a supernova remnant or a pulsar, which meant they must have been created by another type of source. This required scientists to think outside the box and propose some other, less traditional ways that particles could be accelerated. And with that, they recognized what could be described as nature's ultimate particle accelerators: black holes. The idea that black holes could produce high-energy particles had been discussed way back in 2009. Named the Barnardos Silk West effect, after the scientists who came up with it, it describes a phenomenon where if two particles move towards a black hole and collide near the event horizon, they could reach near unlimited energies. However, this theory was thought to be effectively useless, since the particles would no doubt be sucked into the black hole and lost forever. That was until more recent years, when newer models revealed that a fraction of the particles would more likely be ejected back out into space. Free of the black hole, these particles could travel through space as none other than cosmic rays. Now, we've discussed some of the theory behind cosmic rays and where they come from, but it begs the question, what have we actually found? The main thing to understand about this search is that it's really hard. LASSO may have identified 12 candidate Pevatrons in our galaxy, but finding the actual object responsible is a whole other task. That aside, the search is still ongoing, and a few sources have been found. So without further ado, let's take a look. One of the first objects pinned down may be familiar to you, the Crab Nebula. Known as Messier 1, it's a supernova remnant found around 6,500 light-years away in the constellation Taurus. Although stunning to look at, Messier 1 is not just a pretty face. It's capable of accelerating electrons to a quadrillion electron volts of energy. And as one of the best studied objects in the known universe, observing Messier 1 gives astronomers a good insight into how nature's particle accelerators work. In the gamma ray domain, Messier 1 shows some extreme variability. It produces intense flares which can last anywhere between a few hours to a few days, and with our new understanding of Pevatrons, scientists realized that these flares were the photons resulting from some serious electron acceleration. Exactly how this happens has been debated. It could be DSA at the boundary between the particle wind and the medium surrounding the pulsar, energy released by magnetic field lines breaking and reconnecting, or a more complex mechanism within the particle wind itself. For context, electrons at high energies transfer part of their energy to background photons, boosting them to gamma rays that scientists can detect. However, accelerating electrons is really difficult because they lose energy very quickly. To produce gamma rays with energies of a quadrillion electron volts, the electrons themselves must have had several times that energy. This proves that Messier 1 is undoubtedly a Pevatron, and an impressive one at that. However, this has only been proven for electrons, making Messier 1 what scientists call a leptonic accelerator. But Pevatrons are capable of accelerating any charged particle, and if you remember, cosmic rays are mostly protons, so it's these Pevatrons otherwise known as hadronic accelerators, that scientists are most keen to find. I mentioned that LASSO detected a photon at 1.4 peta-electron volts, the highest energy photon ever observed. With such mind-blowing energy, scientists were keen to see where it came from, which led them to our next candidate, the Cygnus region. The Cygnus constellation is one of the most recognizable in the northern sky, spanning more than 800 square degrees or 4,000 full moons. And it was here that scientists found some seriously interesting stuff. LASSO found lots of peta-electron volt photons inside the Cygnus cocoon, a huge superbubble which surrounds a region of massive star formation. Inside the bubble is a massive young star cluster known as the Cygnus OB2 association. This is a very active place, and the many young, massive stars can create a strong wind which accelerates particles. Cygnus OB2 is found nearly 5,000 light years from Earth, and it lines up pretty well with some of the gamma rays observed by LASSO. But as I mentioned, these gamma rays only indicate the general direction of a Pevatron, not its distance, so scientists can often struggle to identify the origin of a signal among several possible sources, and in the case of Cygnus, there are plenty of energetic objects to choose from. In a similar direction to OB2 but further away, there is an X-ray binary known as Cygnus X-3. It consists of a donor star and a compact object, likely a black hole or neutron star. The donor is a Wolf-Rayet star, meaning it is extremely hot and massive, and it feeds material into the compact object through strong stellar winds. This, combined with the compact object, which releases powerful jets of plasma, creates the perfect conditions for particle acceleration. At first it seemed impossible to tell which system LASSO was detecting peta-electron volt signals from, but on taking a closer look at the signal itself, scientists noticed something unique. There was a temporal feature of the signals, a pattern that repeated every 4.8 hours, seen not just in the gamma rays, but in the X-rays and the infrared radiation too. But where was the pattern coming from? On further investigation, scientists realized the truth. Every 4.8 hours, the black hole of Cygnus X-3 orbits its massive donor star. Suddenly, scientists could be certain the gamma rays were coming from Cygnus X-3, and that they had found another Pevatron. Cygnus X-3 was a particularly intriguing object. For one thing, the highest energy photons from this object already measured 3.7 peta-electron volts. And since photons are radiated by accelerated protons, the energy of the proton must be several times larger. What that suggests is that Cygnus X-3 is not just a Pevatron, but a super Pevatron, capable of accelerating protons to at least 10 peta-electron volts. We've had a whistle-stop tour of some of the most exciting Pevatrons we've found so far, but what does the future hold for this ultra-powered search, and where will it take us? Hunting 12 candidate Pevatrons seemed hard enough, but since LASSO's first finding, that number has boomed. LASSO published the first global catalogue of galactic Pevatrons in 2023, detailing 43 ultra-high energy gamma ray sources. But now, 2 years later, and with continued monitoring from observatories around the world, the number of sources has risen to more than 75. With so many candidate Pevatrons hiding in our Milky Way, we need to seriously rethink our perception of the galaxy and what it's capable of. Many thought that the Milky Way was a relatively peaceful place, since it lacks the massive black holes typical of galaxies with violent, energetic pasts. However, LASSO's work has proven this to be an outdated assumption, and is changing the landscape of our non-thermal universe, starting with our own cosmic home. It's definitely an exciting time to be hunting cosmic rays. LASSO is collaborating with several other observatories detecting high-energy gamma rays around the world, including the US, Germany, Namibia, and Spain. This international network has fostered an open and collaborative approach to their experiments, sharing data and corroborating evidence. Their goal is to build up a comprehensive spectrum of photons across different energies, as well as measuring X-rays and gamma rays above Earth's atmosphere. I want to give a huge thanks to Professor Kao for his expertise on the world of high-energy astrophysics. As I'm sure you'll agree, studying Pevatrons is a dynamic and rapidly developing field, and observatories like LASSO are on the front line. Their work so far has transformed our galaxy from a tranquil place to a violent, energetic mess, filled with particle accelerators more powerful than anything we can build here on Earth. We may still be under attack from cosmic rays, but now we're ready to chase them back to their hiding places. Thanks for watching. If you've been enjoying Astrum's videos and want to help keep this channel thriving, I want to ask you to take less than a minute to check out the Astrum Patreon. It's not just ad-free videos, but it's a way to make Astrum's videos less reliant on sponsors and algorithms. The link is below. Your membership directly helps ensure that future videos can stay independent, high quality, and consistent, created for curiosity, not clicks. Thanks so much for considering it. I'll see you next time.